Hello and welcome back. In this video, we will be deriving an alternative curvature formula. So this is easier for some situations, especially if you're, say, using a computer algebra system. And this method is only going to work under these assumptions. So where our derivative is everywhere non-zero as well. So this was already an assumption. We wanted our curve to be smooth. So remember, that means the velocity is never zero. And then we also want our acceleration to be never zero. That's the only way this formula is going to work out. But under these assumptions, we can come up with a really nice formula for curvature. So make computing it especially easy in these circumstances. So some things we need to remember. So if u and v, so these are just two general vectors. This is true in general. If u and v are orthogonal, then if u and v are parallel to each other, let's say if they're parallel, that's what I want to say. If u and v are parallel, so that is if u and v are scalar multiples of one another, then if we compute their cross product, u cross v, will be the zero vector. So that's one thing to remember. Remember, you can think of u cross v, the magnitude of u cross v, being the area of the parallelogram made by putting u and v together. If they're parallel, then that area is zero, and we get the zero vector out here. So that's one thing to remember. Another thing to remember, and I'm going to rederive this, is that if my vector valued function, if it has constant magnitude, then it and its derivative are orthogonal to one another, are perpendicular to one another. So this is, I'll do this for the specific instance of our unit tangent vector and the derivative dt dt. So let's rederive this. So I want to show that t, the unit tangent vector, and dt dt, which I'll just say is t prime here, that's another vector, are orthogonal, perpendicular at all times. So why is this true? It's true because this has constant magnitude. So this was an example we did before, but I'm going to rederive it. The idea is to look at, so if t has constant magnitude, it's just, its magnitude is 1. So that means that t dot t, remember, if I dot product a vector with itself, I get the square of its magnitude, is t squared. So if I now take a derivative, and the idea is the magnitude of t, right? We know what magnitude of t is. It's just 1. So this t dot t is everywhere 1. So if I take a derivative of everything, so if I take a derivative with respect to time, or my parameter t, of t dot t, this will be 0, because the derivative of a constant is 0. And then dt of this, I can use the dot product rule for derivatives of vector valued functions. This is derivative of the first dot the second plus the first dot the derivative of the second. And I know that that's equal to 0. I know dot products are commutative, so this is 2 t prime dot t. That's equal to 0. I divide both sides by 2, so I recover that t prime dot t is equal to 0. And remember this dot product, if I take a dot product between two vectors and I find that it's 0, I know that these are orthogonal. So t and t prime, or dt dt, are orthogonal. So that is the angle theta between t and dt dt is 90 degrees between these two vectors, t and dt dt. So that's going to be important. All right, so with this preliminary stuff, let's start trying to find this alternative curvature formula. So what this comes from, it's not going to be clear why I'm going to look at it, but what I'm going to look at is magnitude of v cross a. So I want to look at magnitude of v cross A. And actually, before I do this, I am going to write my acceleration vector in a funny sort of way that's going to make this work out really nice. So another sort of preliminary thing here is I first want to express velocity in terms of my unit tangent vector. So let's remember that my unit tangent vector t is it's the derivative of, or rather, unit tangent vector t is the velocity vector times 1 over the magnitude of the velocity vector, right? It's points in the direction of velocity, but has unit length, so we get this form. What that tells me then is v, my velocity vector, is magnitude of velocity times my tangent, my unit tangent vector. So that's velocity. If I now take a derivative of this, so now take a derivative with respect to time of both of these, v equals derivative with respect to time of this scalar function, right? Velocity is not a constant. This is a scalar function times, right? It's scaling this unit tangent vector, which is also a vector, or this time, which is a vector valued function. So we have a scalar valued function, multiplying a vector function, vector valued function. And so we can use the product rule for derivatives of this form, scalar times vector. And it's derivative of this scalar valued function, so derivative of v prime, magnitude of v prime, multiplied by t, tangent vector, plus the magnitude of v, scaling dt dt, the derivative of my unit tangent vector. And I'm going to, so that is dt d dt of v, and that's the same thing as acceleration. So here is an alternative, albeit strange, expression for the acceleration of an object in terms of velocity, magnitude of velocity, its derivative, and the unit tangent vector. All right, so I'm going to use that over here. Like I said, this is really, the whole formula comes from looking at magnitude of v cross A. So this is magnitude of v cross, and I'm going to express A here, magnitude of v prime times the unit tangent vector plus magnitude of v times t prime, derivative of the unit tangent vector. So maybe I'll keep this as dt dt. Taking the cross product of those. I'm going to use cross product rule here, so I can bring this v cross through to each one of these. This is a scalar quantity. This is another scalar quantity, so I can pull those out of each cross product. So going back to the algebra of cross products, if you need to, make sure you go back to that in chapter 13 and review how you can use algebra with cross products. So I'm going to pull this scalar out. So this is magnitude of v prime times v cross t plus magnitude of v times the vector v cross dt dt. All right. Let's see, where can we go from here? Right, so where can we go from here? Well, I want to remember those preliminary things we did, that t and dt, so t prime, are orthogonal to each other. I know that, but I also have v here and dt. So perhaps I can make this v look like t, right? We know there's a relationship between v and our unit tangent vector. Oh, I forgot my arrow here. Remember, v is magnitude of v times the unit tangent vector. So I'm going to go ahead and replace that over here. So I have magnitude of v, take a derivative of that, v cross t, plus magnitude of v on the outside here. And then this v here I'm writing as magnitude of v times t. So that's another magnitude of v coming out. Let me just write it like this. How about magnitude of v times t? And then I'm crossing that with dt, or t prime. So maybe I'll write that as t prime here. Same thing. This one's a little bit more explicit than the other. Okay, so that's interesting. Maybe, or maybe you don't think much happened there. Well, I know t and t prime are orthogonal to each other. So that means something in terms of the cross product. We'll get to that in a second. And then over here I have v and t. So remember, v is a scalar multiple of t that we just used, right? V is magnitude of v times t. So that means v and t are parallel to each other. So that's another thing that we get from this computation we did here, is that v and t are parallel. Right? Of course they are. The unit tangent vector points in the direction of v, but has unit length. So of course they're parallel to each other. And that means, remember we talked about over here, that if two vectors are parallel to each other, where did I say that? If u and v are parallel, then their cross product is the zero vector. So this v cross t, this is really just the zero vector. So when I multiply that by v prime, this all goes away, right? So this whole thing now is actually just the zero vector. So I add it to that, I just get this. So let's go ahead and simplify this. That whole term goes away. And I just have, and now I can pull out this other magnitude of v. I have magnitude of v squared, so that's pulling this out of here. Again, you can refresh your memory on algebra of cross products. T cross t prime. And this is still all under a magnitude. I can pull this magnitude out of the other magnitude. So I have magnitude of t cross t prime. And t prime are orthogonal. So remember, t and t prime are orthogonal. So that is, the angle between them is 90 degrees. And remember, the magnitude of a cross product can be expressed in terms of the magnitudes of the two vectors. Right? It's the product of their magnitudes times sine of the angle between them. But if the angle is 90 degrees, then sine of that is just 1. And so this is just magnitude t times magnitude t prime. Remember, this is what makes a square for our parallelogram. And we just get this for the area. So this quantity here, now we have magnitude of v squared times this, which is t, magnitude of t, times magnitude of t prime, which now I'm going to write again as dt t prime. So magnitude of t I know is 1. It's the unit tangent vector, so that's 1. So here I get magnitude of v squared times magnitude of dt dt. So what's my big conclusion from all of this? What did we gain? We now know, so conclusion is magnitude of v cross a is the speed squared times the derivative of my unit tangent vector. All right, we're almost to curvature. Remember what curvature is. So now let's go over here. What is curvature again? Curvature is 1 over magnitude of v times this dt dt, right? This is how we calculated it from before. And so what that tells me is dt is, so dt, times magnitude of dt, my bad. So magnitude of dt is speed times curvature. And I have that quantity over here, so I'm going to go ahead and substitute that, so I have v cross a in terms of curvature. So with that, I get magnitude of v cross a is magnitude of v cubed times the curvature. And here we are, finally at our conclusion. The curvature is magnitude of v cross a divided by the cube of the speed. So what a neat result there. I now have curvature expressed in terms of this magnitude of v cross a and its speed cubed. So cross products are something that computers can do very well. So computationally, this is a very quick and efficient way to compute the curvature. In the next video, we're going to use this formula to find the curvature of some well-known curves. For example, a helix and a parabola. So we'll do that in the next video. Thanks for listening. I'll see you there.